Welcome viewers to the fifth lecture for the online series of lectures for the course of linear algebra. In this lecture, we learn about the definition of a vector space. We'll also discuss vector subspaces. We'll learn about some important results concerning vector subspaces, in particular the properties a subset of a vector space should fulfill to become a vector space by its own right, and hence become a vector subspace. We'll study the definition of linear combinations, and we'll learn about basis of a vector space, and we'll see how we can develop the notion of the dimension of a vector space, okay, through some important results. All right, let's get started with the definition of a vector space. A vector space consists of the following data. One, a field. We all know what a field is. A field, bold-faced F, denoted by bold-faced F, the elements of which will be called scalars. Okay. 2, a set V of objects to be called vectors. 3, a rule or a binary operation called vector addition which associates with each pair of vectors u and v in this set V. A vector denoted by u plus v, meaning that it also lies in the set V, called the sum of u and v, in such a way that for these three vectors u, v and w in the set V, the following are fulfilled. Okay. The first property to be fulfilled for this operation of vector addition is that addition is commutative. Meaning that u plus v is always equal to v plus u. Okay. B, addition is associative, that is u plus v plus w, it means that v and w should be added first to result in a vector called v plus w, and then you add u to that resulting vector to get a final vector, which is denoted by this u plus v plus w, and that should be the same as u plus v plus w. Okay, for the right side, you add u and v first to get a new vector, and that new vector is added to w to result in a final vector, and that should be the same as what we have on the left hand side. This is the associativity of vector addition. Thirdly, there is a unique vector in the set V called the zero vector, such that u plus the zero vector is the u vector for all u in the set V. Okay. Finally, the additive inverse for each vector u in the set V, there is a unique vector negative u belonging to the same set V, such that u added to negative u is going to give the zero vector. Negative u is called the additive inverse of u. Okay, so these four properties need to be fulfilled with respect to vector addition. Alright, now the fourth point is that we have another rule or operation called scalar multiplication, which associates with the pair c comma vector u. Okay, here c is with c belonging to the field F, and u is an element of the set V. Okay, so this operation associates with each pair c comma u a vector c times u in the same set V, called the product of c with the vector u in such a way that the following hold for any c1, c2 in the field F, and u and v in the set V. The first one being the scalar 1 times the vector u is equal to u, and this holds for all u in the vector space in the set V. Okay, the second is that c1 times c2 times the vector u. It means that you have the multiplication operation in the field F, and with respect to that multiplication operation you multiply c1 and c2 first, and that results in a new scalar, which is c1 times c2. You multiply that that resulting scalar with this vector u to obtain a new vector in this set V. Okay, and that has to be the same as C1 times C2 times Cu. So on the right side you have this vector C2 times Cu, and that gets multiplied with this scalar C1 to result in a new vector in the set V. That has to be the same that we have on the left hand side. Okay, the third property is C times U plus V has to be the same as Cu plus Cv, and C1 plus C2 times U should be the same as C1U plus C2U. Okay. Together, the third and the fourth property are called distributive property. Okay. Now, if all of the above are fulfilled by the set, so there are two constituents, remember. Number one was the field F, and number two was the set V. Okay, and these two sets, the field and the set V, are equipped with two operations. One is vector addition and the other one is scalar multiplication. And the vector addition and scalar multiplication should satisfy certain properties which are listed under 0.3 and 0.4. Okay, so if all these properties are fulfilled by the set V and the field F, this field F is often referred to as the ground field. Referred to as ground field. Okay, so if these properties are fulfilled by the set V and the field F, the set V and the field F, we say that V is a vector space over the field F. Okay, good. This was the definition of vector space. Now we'll study some examples of vector spaces. Example 1. The familiar example of a vector space called the vector space of n tuples. The n tuple space denoted by boldface F to the n. Okay, let F be any field and F to the n be the set of all n tuples denoted by V1, V2 all the way up to Vn. So each of these components take its value in the field. Now I have to define vector addition and scalar multiplication in this set f to the n. Okay, so if I have another n tuple w having n components, w1, w2 all the way up to wn, then the addition between these two n tuples is defined as the addition component wise. So v1 gets added to w1, v2 gets added to w2 to yield the second component of the resulting vector, and finally the nth component of the resulting vector is given by, I should have written w, although they are the same, but I should have written w1 plus v1 instead of v1 plus w1, although they are the same, and hence the commutativity of vector addition is satisfied. w1 plus v1, w2 plus v2 all the way up to wn plus vn. Okay, so that's how the vector addition is defined. And the scalar multiplication is defined in the following way: c times v, okay, which is given by c v1, c v2 all the way up to c vn. Okay, important thing to note here is that these additions are addition in F, addition in the field, and this multiplication is in F as well. Okay, F being a field is equipped with an addition operation and a multiplication operation. Okay, so this addition and this multiplication, they are in the field F. Okay, so this is how the set f to the n is equipped with vector addition and scalar multiplication. So I leave it as an exercise for you to check that this set equipped with these two operations is indeed a vector space. You have to check that all the properties listed in the point 3 and in the point 4 are fulfilled. Okay, now our second example is that of the set of all m times n matrices over a given field F. This is example 2. The space of all m times n matrices over F. Okay, it means that the entries of the m times n matrices take their values in the field F, and this space to be so first of all it's a set, then we prove that it's a vector space. This set is denoted by f to the m cross n. Okay, how do we do that? We start with a field. Let f be any field and m and n are positive integers. Let f to the m cross n be the set of all m times n matrices over the field F, the sum of any two vectors. In this case, the vectors are m times n matrices, okay? Matrices of size m times n over F, okay? So that the sum of any two vectors A and B is defined as, okay, A is an m times n matrix, B is also an m times n matrix. So the ijth component of the addition of these two matrices is defined as the sum of the ijth entry of the constituent matrices. Okay, so this addition in the field F, okay, because these are matrices of, matrices defined over F. Okay, and the scalar multiplication. So I have a scalar C, and I multiply this scalar with this vector A, which is of course a matrix of size m times n, with the entries taking their values in the field F. So C times A is a new matrix, and the ijth entry of that matrix is given by C times the ijth entry of the matrix A, and this multiplication is again in F. Okay, so with respect to these two operations, vector addition and scalar multiplications, one needs to verify that all the properties listed in the definition of a vector space are fulfilled, and hence F to the m cross n is a vector space over the field F. So verify that F to the m cross n is a vector space over the ground field F. Okay, I also leave it as an exercise for you. Okay, now the third example is that of a function space. Thus, example 3, the space of functions from a non-empty set S to a field bold-faced F. Okay, so let me denote this space F as script F S comma bold-faced F. Okay, now this is a set the set of all functions from the given set S to the given field F. Okay, so if I pick up two elements F and G from this set script F, then the addition of these two elements here, meaning that two functions, the addition of two functions evaluated at the point S of this set big S, is defined as f of s plus g of s. Okay, remember that f and g are functions from the non-empty set S to the ground field F. Therefore, both fs and gs are elements of, they belong to the field F. So this addition is again in F. So this is how we define the vector addition, and the scalar multiplication of C in F with a given vector F, which is of course a function from the non-empty set S to the field F, is defined as C times F, which is expected to be a function, right? Function here in this set, and this function evaluated at the point S of big S is defined as C times F of S. Okay, again F of S is in F, as we know, and C is a scalar, so this multiplication is in F. Okay, now you got to verify that this set fulfills all the properties of a vector space listed earlier in this lecture, and hence forms a vector space over the field bold-faced F. Okay, so this is the third exercise that you need to do. Okay, good. Now the fourth example. Example 4 is about the field of complex numbers. Okay, the field bold-faced C of complex numbers can be regarded as a vector space over the field bold-faced R of real numbers. Okay, so it can be generalized further. More generally, one can consider the vector space V of complex n tuples x1, x2, all the way up to xn, where all these components take their values in the field of complex numbers. Okay, so this is a vector space. We will see the vector space of complex n tuples over the field R of real numbers. Okay. Okay. Now, how do we define the addition of two vectors? It's done pretty much the same way we did for f to the n. Okay, but it's not the same as f to the n. We'll see. Okay, so I have an n tuple of complex numbers. Okay, or complex n tuples, x1, x2, all the way up to xn, and that gets added to another complex n tuples, y1 all the way up to yn, and the addition of these two complex n tuples is given component wise, x1 plus y1 being the first component of the resulting n tuple, x2 plus y2 is the second component, finally xn plus yn is the is the last component. Okay, and scalar multiplication is defined as, remember that our C now takes its value in the field of real numbers, because our ground field is the field of real numbers. So C gets multiplied with this complex n tuple x1, x2 all the way up to xn, and it's defined as C times x1, C times x2 all the way up to C times xn. Okay, so this multiplication is in the field of complexes. Since C in R can easily be regarded as a complex number. Okay, all right. So this is how we define the vector addition and scalar multiplication in the set V of complex n tuples, okay, over the field of real numbers. These vector space is different from the vector space C to the n. Okay, C to the n is an example of the vector space F to the n. If I take the the field to be the field of complex numbers, then F to the n becomes C to the n. But there, in this case, or in this case more generally, the ground field is F. So in this case, the ground field is C. Whereas here, my objects are the same as here. They are all, in both the cases, the objects are complex n tuples. But the ground field here is the field of real numbers instead of the ground field here, instead of the ground field of complex numbers here. Okay, so that's the difference, and that is why these two vector spaces are also different. Although the objects in both the sets are the same, because of the difference of the ground field, the underlying vector spaces are different. Okay, so that's a very important point to note, that these two vector spaces are different. Okay, now we move to the definition of a linear combination. Linear combination. A vector V in a given vector space V over the field F is said to be a linear combination of the vectors u1, u2 all the way up to un in the vector space V, provided there exist scalars C1, C2 all the way up to Cn such that V can be written as C1 U1 plus C2 U2 plus all the way up to Cn Un. Okay, so in the summation notation we write it like this, right? So this is the definition of linear combination of vectors from a given vector space. Okay, all right, so we'll see uses of this definition later, but before that, before we need to verify a few simple facts using the definition of vector space. So the first being C times the zero vector, where C is just a scalar, okay, is equal to the zero vector itself for any C in the field F. Okay, so how do we see it? First, write C times the zero vector as C times the zero vector plus the zero vector. Okay, since zero vector is equal to the zero vector plus zero vector. Okay, and using the first distributive property, which is property 4C, we can write it as C times the zero vector plus C times the zero vector. Let me write it here by using 4C. Okay, so now the task is to add the additive inverse of this guy on both the sides, which is negative C times the zero vector. I add this vector on both sides, and then, by invoking associativity on the right side, then, from the property 3D, we see that this is nothing but the zero vector, and this is again zero vector added to C times the zero vector. Okay, and the zero vector added to C times the zero vector is C times the zero vector, which is the property of the zero vector, right? This is what we needed to prove. QED. Okay, so the first simple fact has been verified using the axioms of a vector space, axioms satisfied by the vector space. The second simple fact is that is -1 times the vector u is negative u. Okay, no, I think this is the third one that I need to check. Let me first try to see how we get 0 times vector u is the zero vector. Okay, where this 0 on the left side is the scalar 0. Okay, and the zero vector on the right side is the zero vector. So I see it this way: 0 times the vector u is the same as 0 plus 0 times the vector u. Okay, why is it so? Because 0 plus 0 in the field of scalars is just 0, the scalar 0. Okay, now again using the distributive property, which is 4D, I guess. yes, for D, we have this to be 0 times u plus 0 times u. So this is by using for D. Okay. So now I add negative 0 times u on both sides. Okay. And then invoking associativity on the right side, we get, so this guy is nothing but the 0 vector. And on the right side, I have 0 times u plus the 0 vector, which is 0 times u, right? Therefore, we get 0 times u is the 0 vector. So this is how we see how this holds. Now the third simple fact is that negative 1 times the vector u is equal to negative u, the additive inverse of u. Okay, so we have seen in 2 that 0 vector is equal to 0 times u, okay, which implies that the 0 vector is 1 minus 1 times u. So this is happening in the field of scalars, okay. And by using the second associativity property, that is for D again, okay, for D, we can write it as 1 times u plus minus 1 times u. Okay. Now adding minus u on the both sides, minus u, negative u on both sides. Okay, we know that 1 times u is just u, right? Which follows from 4a. Okay, so this is, so I add negative u to u, and then I have this guy minus 1 times u. Okay, good. So that, from the property of 0 vector, we know that the left hand side is just negative of u, negative u. Okay, and on the right side, this is the 0 vector, and 0 vector getting added to minus 1 times u, which is simply minus 1 times u. Okay, so therefore we get that negative u is equal to minus 1 times u. Okay, good. So now I suggest some exercises for you from the book by Hoffman and Kunz. Let me list those exercises. Suggested exercises. Page 33. Hoffman and Kunz. problem number 1, 2, 3, 4, 5, and 7. Okay, good. All right, so I just try to solve one of the problems here, problem number 3. Okay, problem number 3 asks me to find, so I'm given three vectors in C3. So C3 is the vector space. Okay, C3 is the vector space, and I'm given 3 vectors, 1, 0, minus 1 in C3, 0, 1, 1, and 1, 1, 1. Okay, these 3 vectors are given in C3. I have to find which vectors in C3 are linear combinations of these 3 vectors. Which vectors in C3 are linear combinations of the above 3 vectors. This is the question. Okay, so let me write so we know the definition of linear combination. We take the linear combination of these 3 vectors, C1 times 1, 0, minus 1 plus C2 times 0, 1, 1 plus C3 times 1, 1, 1. Okay, so let me call this linear combination of these 3 vectors z1, z2, z3. Okay, that is a vector in C3. Okay, so now the left hand side has to be the same as the right hand side, so we get a system of linear equations given as follows. C1 okay, I have to check the question. So I think this is, what was the question? So let me check the question. This is problem number 3. Page number 33. Page 33. Okay. 1, 0, minus 1, 0, 1, 1, and 1, 1, 1. Good. Okay. Let me get back to where we were. So we are good. So the first equation is C1 plus C3 is equal to Z1. And the second equation is C2 plus C3 is equal to Z2. And finally we have minus C1 plus C2 plus C3 is equal to Z3. Okay, so this is the system of linear equations that we have. Okay, now we form the augmented matrix. Okay, the technique that we have learned in the first part of this course. So the augmented matrix corresponding to this system of linear equation is 1, 0, 1, Z1, then 0, 1, 1, Z2, and minus 1, 1, 1, Z3. So this is the augmented matrix. Okay, so we try to reduce this augmented matrix and put it in row reduced echelon form. So the first operation is going to be R1 plus R3 is equal to R3 prime. That gives us 1, 0, 1, Z1, 0, 1, 1, Z2, and then 0, 1, 2, Z1 plus Z3. Okay. And then we are going to do minus R2 plus R3 is equal to R3 prime. To reduce it further, 1, 0, 1, Z1, 0, 1, 1, Z2, and then 0, 0, 1, Z1 plus Z3 minus Z2, Z1 plus Z3 minus Z2. Okay, we don't need to do any more steps. Why? Because we see that this is always consistent. If we had a 0 here, if we had all these entries to be 0 and an expression containing Z1, Z2 and Z3 on the in this position, then we would have a consistency condition for this consistency condition, so that the system is consistent under that condition. Okay, we would have a condition. But here, since we don't have all these entries to be 0, in particular the last entry here is non-zero, the system is always consistent. Okay, which means that which tells us that the system that we started with admits a solution no matter what you take for what you choose for Z1, Z2 and Z3. Okay, it means that any vector in C3 is a linear combination of the vectors 1, 0, minus 1, 0, 1, 1, and 1, 1, 1. Okay, good. Now we need to define vector subspace, but before that we take a break. Thank you for attending the first segment of the 5th lecture.